Good afternoon, everyone. My name is Santa Ono. Welcome to University Hall. And I'd like to thank all of you for joining us at this special event to honor the members of our faculty who are truly leaders and best, if you use a University of Michigan motto. And I'd especially like to thank our provost, Lori McCauley. She's also the Executive Vice President for Academic Affairs for her leadership in making today possible, as well as our moderator, Michael Solomon, who serves as the Dean and Vice Provost for Academic Affairs at the Rackham Graduate School. Most of all, I'd like to congratulate our three awardees, Professor Karen Smith, Professor Joel Slemrod, and Professor Lutgard Raskin, who goes by Lut. These three outstanding members of our faculty come from diverse fields: mathematics, economics, and engineering. But what unites them is the same set of values that brings us together as a community here at the University of Michigan: a deep and restless curiosity, a relentless pursuit of excellence, and an unwavering commitment to integrity. These professors, like so many of you across our university, either here present or watching on streaming video, are leaders in their fields. These professors are dedicated to shaping our future through innovation and discovery. And just as importantly, they are committed to our students, to teaching, developing and mentoring our next outstanding generation of scholars, servants, and leaders. Together, they're impacting our state and shaping our nation. Even more, they are demonstrating why we at the University of Michigan are a pinnacle of higher education and an inspiration to institutions around the world. Thank you to all three of you, and congratulations again. It is now my privilege to invite Provost Lori McCauley to the podium to introduce our first lecturer. Lori?
Thank you, President Ono. There's only one thing better than engaging in great science, and that's celebrating it with colleagues. And that's what we're here for today. And it's my pleasure to welcome you and to introduce to you the distinguished university professors whose lectures this afternoon will certainly leave you with much to discuss during the reception that follows. This lecture series represents an exuberant celebration of the power that ideas possess to excite and unite us. Elevating the scholarship of thinkers like Karen Smith, Joel Slemrod, and Lutgard Raskin is one of our institution's core purposes and promises. That purpose is always humming in the background, but we all cherish days like today when we can bring that purpose to the celebratory forefront. To that end, it is now my pleasure to introduce Karen Smith, the William Fulton Distinguished University Professor of Mathematics in the College of Literature, Science, and Arts. Professor Smith is a brilliant mathematician whose research is in algebraic geometry, one of the oldest areas of mathematics. She's a recognized world leader in understanding the field from a theoretical perspective. Her research has received continuous support from major funders, including the National Science Foundation. Professor Smith, a University of Michigan faculty member since 1996, has published 4 books, including a classic introduction to algebraic geometry, and her articles appear in the leading journals. An impassioned advocate for inclusivity, she works to improve climate in the mathematics department and more broadly. She's transformed undergraduate courses, served as associate chair for graduate studies, and supervised 20 doctoral students, including many from backgrounds underrepresented in mathematics. She edited the American Journal of Mathematics and Advances in Mathematics and is invited to give major lectures, including the 2021 American Mathematical Society Annual Joint Meetings Colloquium Lecture. Professor Smith, a winner of the AMS Ruth Lytle Slater Prize in Mathematics, is a member of the American Academy of Arts and Sciences and the National Academy of Sciences. I'm pleased to invite Professor Smith to present her lecture.
Thank you very much. Can everyone hear me? I'm afraid this is going to slide off. I'll put it here. All right. Thank you for the wonderful introduction and for the honor. And I'm grateful I see many of my colleagues and family and friends and students. So thank you for coming. I'm trying to talk to people that are not in math. So I hope I succeed. Feel free to ask me afterward. I'll try to clarify if I've failed on my slides. And all of the beautiful pictures you see on my slides are all due to Herwig Hauser, who is a friend of mine in Vienna, who's produced these pictures. You're going to learn something about what they mean in this talk. So before we get to the math, I wanted to have a short tribute to the person my professorship is named after. This is William Fulton, who is a professor emeritus at University of Michigan and a renowned algebraic geometer. So my talk is in algebraic geometry. He's a geometer, and I learned a lot from him, and he's a beloved mentor and colleague. And that's why I chose to, also somebody I admire very much, I chose to name my professorship after him. But I also wanted to point out, because this is the geometer, and I'm an algebraic geometer, here is another distinguished university professor at Michigan from whom I learned a lot of algebra. This is Mel Hochster, who is a long-term leader of Michigan math and also Oscar Zrisky Distinguished University Professor. All right, so let's talk about some geometry. I think geometry is the oldest subject of mathematics. I'm not going to include accounting. I'm sure people were trading with pebbles and things maybe before they were thinking abstractly about lines and circles and points and shapes. But geometry, as you can see, I don't know how old it is, but there's at least evidence 5,000 years ago people were thinking about abstract geometrical objects like lines and circles and cones and even conic sections. And then about 2,000 years, a little more than 2,000 years ago, in ancient Greece, there was as everyone probably knows, a classical civilization which developed mathematics and philosophy and many other things very deeply. And Euclid's Elements is the most famous textbook in geometry. Actually, I read it's the second most printed book ever after the Bible. And until the 20th century, when public education became a thing and people started making textbooks for kids, all educated people apparently were expected to have read some of this geometry textbook. And it's a very interesting textbook. This is geometry. I do algebraic geometry. Oops, sorry. Might destroy my microphone. I do algebraic geometry, though, and that was not possible until Descartes came along. So Descartes, which I'm pronouncing wrong probably, there's less T in it, I think, right? If you speak French, invented Cartesian coordinates. So you know how you have the XY plane, you've studied it in high school, and that was René Descartes who invented that, and that's what makes it possible to write down algebraic equations that describe the geometric shapes. So you guys probably know from high school how to write down a line in Cartesian coordinates, and there I've got one up there. And maybe you remember how to write down a circle as well. And probably you may have had a multivariable calculus class where you did a 3D cone at some point. So you could do Cartesian coordinates in 3 variables, 4 variables, any number of variables. And once you do that, you can start talking about parabolas, which the Greeks would have thought of as just a intersection of a cone and a plane. You can start thinking of them by giving an equation for them, choosing some coordinates and writing down equations. So these are all examples of ways of writing down geometric shapes using algebra. That's what algebraic geometry is, studying geometric shapes with algebra. So algebraic geometry is the study of particular kinds of geometric shapes that are defined by polynomial equations. So polynomials, these are examples of polynomials here, where I have like maybe some exponents on my x and y, or my z, or however many coordinates I have. I don't have things like a cosine or a sine. This would not be a polynomial. So right here, this is the graph of y equals cosine x, which you might remember as well from some class a long time ago. This is not something we study in algebraic geometry because it's not given by polynomials. It's given by trigonometric functions. These are all objects that belong to algebraic geometry because they're all defined by polynomial equations. Now this one, which most people do see in high school if they took an advanced pre-calculus class, we usually graph it using sine, but there's a way to write it also using polynomials. So you may have seen this kind of a rose shape when you studied trigonometry, but you can also, many of them, write actually with polynomials. So these are examples of the kinds of things on the top of the slide that belong to the subject of algebraic geometry. So let me now make a definition of a precise definition of the actual objects we study in algebraic geometry. We call them algebraic varieties. A variety is a shape. An algebraic variety is a shape that is defined with polynomials, polynomial equations. So, back. So these four shapes that are on the black background are all shapes defined by one polynomial in 3 variables. So this shape is where x times y times z is 0. You see we get 3 planes. The x equals 0 is one of the planes, the y equals 0 is another one of the planes, and the z equals 0 is another one of the planes. That's about as simple a shape you could do. That's not just a plane, I suppose, in 3D. Then we have this sort of cooling tower, which is given by a polynomial like this. This slightly more complicated shape, which you can see, is given by a slightly more complicated polynomial. As the algebra gets more complicated, so does the geometry. So in this purple shape, we see it's coming from a polynomial which has a degree 4 component. Y squared z squared, that's a degree 4 term. It's a more complicated polynomial. And here's another one, again, one polynomial, and sorry, that minus should say equals. This is where the x coordinate squared is equal to the y coordinate squared times the z coordinate. That thing called the Whitney umbrella right there. This one, that's not as beautiful because it wasn't made by my friend who's really talented, but by myself, is defined by 2 polynomials. This is still a 3D shape. It's a union of a plane and a line. It's a union of the z equals 0 plane and the line where x and the y coordinates are 0. It's a z-axis. So these are all examples of being in 3-dimensional space. And we call these surfaces because they're 2-dimensional algebraic varieties. Now, you have to imagine we, most of the time, are studying an arbitrary number of polynomial equations. I could have 17 different polynomial equations in 23-dimensional space, cutting out some object which is maybe parametrizing something of interest to somebody in mathematics or engineering or something else. So these are the most simple things we can imagine, and that's basically all our puny human minds can draw a picture of, or even with the assistance of the computer. But an algebraic variety can be in any number of dimensions, cut out by any number of equations. It's actually a theorem that if you had even an infinite number of equations, there's actually a finite number that would work. The famous theorem of Hilbert from 120 years ago. So there are finitely many equations, but still, it could be very, very large. So that's a definition. Mathematicians like definitions. This is the definition of my subject. Algebraic varieties are everywhere. This is just a tiny sampling of where they are. So I study algebraic geometry and algebraic varieties because I think they're inherently interesting. I'm not particularly studying any particular application. However, All throughout mathematics, other mathematicians use algebraic geometry as a tool for studying whatever they're interested in. So maybe you're interested in groups, like Professor Ono's dad was, a mathematical group. Mathematical groups are very often described as algebraic varieties. You can cut them out with polynomials. Or maybe there's a parameter space of groups which happens to have the structure of a variety. So other mathematicians study algebraic geometry as a tool, but also physicists do. You might have heard of string theory. There's varieties that come up there as different kinds of string theory concepts. And they're, of course, all over engineering. Error correcting codes, which is the technology when you have a disk, like a CD or something, and you want to, it gets a scratch on it. So when you plug it in, you hear the music anyway. That's because we use algebraic varieties and other tools to figure out what was the intended message from using algebraic varieties. So it's all over the digital world. It's all over computer-aided design. So I just plucked this off of a website. This is created from a computer-aided design program. This razor is piecewise little pieces of algebraic varieties. It's approximate, like in every little chunk is a little piece of an algebraic variety. And actually Pixar does things like that too. And so it's used in engineering and art and design. And this table here is made out of an algebraic variety on the bottom. Actually, the top two, because a plane is the simplest kind of algebraic variety. So you can use algebraic geometry in many places. But again, I'm doing it for its own intrinsic interest. All right. Actually, maybe I should say something about why we use varieties rather than polynomials, rather than some trigonometric functions or exponential functions or other kinds of functions. It's because they're easy. A computer can handle multiplying and adding and combining polynomials. And so can we, by hand, much more easily than some crazy function that's going all over the place. On the other hand, polynomials also approximate all kinds of other functions very, very well. So we can approximate things with tools that we can actually manipulate pretty easily if we work with algebraic varieties and polynomials, polynomial equations, to cutting out these shapes that are given by polynomials, or in many cases, piecewise polynomials. There's no one polynomial function, I don't think, that would define this thing, but piecewise, maybe the boots are from one thing and the hat from something else, so forth. All right, so they're everywhere, but I study them for their own intrinsic interest. And one of the most interesting things about them is they can be smooth. So on these slides, everything you see here is an actual algebraic variety defined by one polynomial in 3 variables. The 3 variables tells you it's a 3D shape, it's in 3D space, right? And so that black background is sort of our 3D space, and each of these is given by one polynomial. And what you can see is these top ones are all smooth, right? There's no places where it's pinched or turned on top of each other, or like somebody tied a string around it and squeezed it, or made like a poke in it, right? These ones on the bottom here are singularities. So you can learn the title of my talk right now. These are what we mean by singularities, these points where the variety, the geometric object cut out by polynomials, has like a sharpness to it. It's not smooth. A sharpness or some other weird thing. Like on this one, which is kind of interesting, you get these 2 lines that are kind of squeezed in on this thing. Or you get this croissant here where that's a singular point where those 2 things come together. So these are the singular varieties that are much harder from a theoretical point of view to handle than these ones, where you have lots of other tools of mathematics to work with, like tangent planes, and multivariable calculus could work nicely here, differential geometry. But down here, we have singular things. But these do arise in nature, or at least in applications to mathematics and physics and things. And you might want to model a lemon. So these do come up, and they're important, and we need to understand them, even though they're more difficult. One thing, this is a theorem that is not too hard to prove, actually. If I look at the set of the points on my variety. So like on this guy here, if I look, there's these 3 singular points here. The singular points always form a variety themselves. So a union of 3 points, you can define that with polynomials. You know, x equals 0, y equals 0, z equals 0 defines the point 0, 0, 0 in 3 space. So I can define, the singular set is always a subvariety, which is a helpful thing to know. And it's a strictly smaller dimension subvariety. So most of our points are smooth, but we would like to understand these singular ones. All right. So how do we do that? What kind of questions do mathematicians in algebraic geometry work on? Of course, I'm only going to tell you a tiny subset, but here is an idea. The big question is, how can we understand and deal with the singular points on an algebraic variety? So for example, if I look at that union of the 3 planes, you can kind of really understand that thing as a union of 3 smooth things, right? I can just kind of separate those 3 planes out into 3 separate planes. So this variety here is a singular variety because along where those planes intersect, it's like crossing on itself, somehow not perfectly smooth. But yet, somehow it's very nice and easy to understand that I could sort of just like, maybe if I lived in 5D or something, just separate those planes apart. Right? And in fact, that's true. That's the simplest kind of singularity we got there. And here we see some slightly more complicated ones. It's not so clear we could iron that little weird place out where it's requiring a singularity. And it's not so obvious we could somehow unravel this thing that's all twisted up on itself. But this is a major question in algebraic geometry, is can we separate out, smooth out, or unfold singularities? And this is one of my favorite theorems in mathematics. I'm going to tell you about it on the next slide. But this is a big question. Can we do this? We'll see a theorem in a moment. But another thing we can ask is there some way to decide that some singularities can be ignored? So in this one, like I said, we can easily imagine we could ignore that singularity by sort of separating out those planes. And there's other situations where tools from differential geometry or some other subject can be applied to smooth varieties, and they can also be applied to some sort of negligibly singular varieties. So you can kind of try to quantify what it means to be negligibly singular and try to understand when you have such a thing. Or, even more detail, you can try to assign a number to each singularity and say the bigger the number is, the more singular it is. Or maybe the smaller the number is, the more singular it is. Or something like that. Can we quantify the singularities? Is there a way to say this singularity is twice as bad as that one? And these are all the kinds of questions that algebraic geometers think about. Or actually, this is just one subfield of algebraic geometry, really. But this is the kind of questions in my subfield of algebraic geometry. And this is a little bit of a novel question that I've been thinking about recently, is if we do have a way to quantify them, and pro tip, we do, that means there's a way to say what this is the value, the measure of the worst singularity. And now, what does that worst singularity look like? What is the worst possible singularity? And yeah, I'm not going to be able to have time to tell you about all of this. What I'm going to do is tell you about the answer to the first question. OK, so moving ahead. This is what it means to be a resolution of singularities. So this looks like an actual math slide. So my apologies for the non-math people. It's taken from an actual math talk. But you can handle it. I'm defining what it means to be a resolution of singularities. So instead of looking at the slide, you can look at the slide, but what I want you to imagine is we have a variety in the plane. Here's my plane on the floor, and it's just a curve, like a piece of wire in the plane. I just have a piece of wire crossing itself, and that's what we see right here. Oops, that's not what I wanted to do. Why is this not working? There it is. This is my plane, the floor, and this variety V here, this black curve, looks like an alpha or a fish. That's a piece of wire. Imagine that's a variety in the plane. And a resolution of singularities means just thinking in this 3D space here, I can easily resolve that singularity because I can pick that piece of wire up into 3D and stretch it out into a nice smooth wire, right? And in this picture, we have our curve y down in the plane, and this is, by the way, the equation for it, if you wanted to write down a polynomial equation defining that curve. And up here in 3D is the unraveling. I'm picking up that wire. This black S here is just picking that up into 3D. That curve B is in 3D, and so it needs at least 2 equations to define it. And these are its equations. It doesn't matter specifically what they are, but just so you can see them, that is this curve. And this is a resolution of singularities, because that's really almost the same variety, right? If I take that piece of wire and I smash it back down to the plane, in other words, I project it back down to the 2-dimensional space, it lands exactly on my curve, my original curve V, the singular curve. And everywhere except where I had the singular point, so you see I have a singular point right there where the curve crosses itself. Everywhere else, this is a 1-to-1 map. Every point on this B has exactly 1 point down here on V. Every point has exactly 1, except right over that, there's 2 points, 1 here and 1 here. That's why this thicker brown line is here, to show you that this point and that point are 2 points that go to this. So above the singular points, it's different. But above the smooth points, it's exactly the same. That is a resolution of singularities. And that is the definition. And this resolution of singularities is just that smashing of that nice S curve down onto our alpha curve. So, does every variety have such a thing? This is not at all obvious. I have 1 minute? That went fast. It's not at all obvious that you could have every single variety have this. Singularities can be crazy bad, but in fact, it is a theorem. And it's a theorem that won a Fields Medal. And it's the theorem that every variety, no matter how singular it is, there's a smooth variety that looks just like it mapping to it. And this is a picture where you can kind of see what's happening. In this picture, I see the cone upstairs, the cylinder upstairs, twisting down to give me the cone. You can imagine it twisting. But if I embedded that cone in a 5D space, I could actually see it as, again, a projection. And you could always do a resolution of singularities as a projection. That is the theorem of Hironaka, which is an amazing theorem, my favorite theorem in math. Now, we were talking only about varieties in a real space. You could also do algebraic geometry in other exotic spaces, like over finite fields, and we don't know this theorem there. Open question there. So that is, I hope, a takeaway that you can imagine you can resolve the singularities of any singularities. And this is just the last slide to show you some of the things that I'm working on and some of the people I'm doing it with. And I think I'm out of time, so I won't say anything more about that. But I'm sort of saying a little bit about what we said on the questions you could study are some of the questions that I've studied. And these are some of the people, just a small bit of some of the people that I've enjoyed doing it with. So thank you.
Thank you very much, Professor Smith, for your lecture. We have time for 1 or 2 questions. And we have microphones around, and also if you're joining us online, you also can ask your questions online, and we'll get them to you here. I'm actually happy to start with one question, which is, so I really understood that this distinction, so thank you for really the clear definition of topics that I have heard about but not understood. This idea about polynomials as a definition of shapes. I understood that polynomials are an easy way to describe other shapes, but are there times in which you really would want to actually be working in the spaces that are these non-polynomials, these more exotic shapes, and why would that be? Yeah,
Definitely that comes up. Trigonometric functions, if you're studying waves, for example, and people do study those, just not, it's no longer algebraic geometry. Algebraic geometry is using polynomials.
Is it important, let me just ask a question, is it important to really focus on polynomials in their own right, or is it really at that point a definition of a field?
I think it's important because it is such a rich field. You can do much, much more with polynomials than you can do with a completely like arbitrary functions or trigonometric functions or exponentials. You can do much, much more with them. And so like a huge field has developed, and they arise naturally everywhere. So the spaces that parameterize other kinds of things. So there are spaces that come, there are shapes that come up in complex analysis called Riemann surfaces. And those are defined using analytic functions, which are not exactly polynomials. But if you have a compact Riemann surface and you want to look at the parameter space of those, so like a space whose points are in one-to-one correspondence with the objects you're trying to study, it turns out to be an algebraic variety in a certain sense. And so it turns out to be defined by polynomial equations. Yeah, it comes up.
Thank you. Thank you. Well, please join me in congratulating our distinguished university professor, Professor Karen Smith, for her lecture. I'd now like to invite up Professor Macaulay for our next speaker.
Thank you, Professor Smith, for putting life into mathematics. I won't look at shapes the same ever again. I now have the honor of introducing Joel Slemrod, the David Bradford Distinguished University Professor of Economics in the Department of Economics and the Paul W. McCracken Collegiate Professor of Business Economics and Public Policy in the Stephen M. Ross School of Business. Professor Slemrod is an authority on the design and effects of tax policies. He has enhanced the understanding of taxation and informed tax structure practices worldwide with his pioneering research on how tax policies influence households and firms. Best known for his work on tax administration and compliance, he found that firms, not individuals, remit 85% of tax revenues, and that compliance costs equal 10% of tax revenue raised in the United States. Professor Slemrod, the founding director of the Office of Tax Policy Research, joined the University of Michigan faculty in 1987. The Office of Tax Policy Research collects and distributes tax data used by researchers, policymakers, and interested citizens. An outstanding teacher and prolific scholar, Professor Slemrod has published nearly 200 scholarly articles and 17 books, including last year's Rebellion, Rascals, and Revenue, Tax Follies and Wisdom Through the Ages. He has testified before Congress, advised the Congressional Budget Office and Internal Revenue Service, and assisted Treasury departments on every continent. He edited the National Tax Journal, co-edited the Journal of Public Economics, and is a past president of both the International Institute of Public Finance and the National Tax Association, which awarded him the Daniel M. Holland Medal in 2012. It's my pleasure to invite Professor Slemrod to present his lecture. Thank you.
Well, thank you for that wonderful introduction. I'm deeply honored to receive this professorship. I chose to honor David Bradford in the professorship. David Bradford was a professor of economics at Princeton University who went out of his way to be kind and encouraging to young scholars like me. He was a true scholar, dedicated to pursuing the right answer regardless of where that took him, and in that way he was my role model. Well, thanks for coming today. Having spent my entire professional life studying taxes, I thought it appropriate to title my talk today, Life and Taxes, after a well-known quotation that you probably all know, that's been attributed to Benjamin Franklin, but apparently Mark Twain said it before him, and many said it before both. In this world, nothing is certain except death and taxes. The enduring resonance of this quotation suggests that taxes are indeed a subject of importance, if perhaps a subject that many people prefer not to think about, like death. It turns out, though, that some of my research actually addresses the connection between taxes and death. I've investigated estate taxes, taxes due on the estate of wealthy folks upon their passing, in particular to what extent estate taxes inhibit the accumulation of wealth. I've studied the costs incurred in terms of poor decisions if one acts counterfactually as if one lives forever. Indeed, my most notorious paper concerns another connection between death and taxes. It investigates whether the timing of deaths around the time of anticipated changes in the estate tax, whether people living a little bit longer can reduce their taxes, or people living a little bit longer, their estate taxes will go up. Does it actually affect when people die? Sure enough, there is a clear, albeit small, pattern of this nature. And this finding has since been replicated in Australia and Sweden. This paper won for me an Ig Nobel Prize, which some of you may know about. It's awarded annually by the Annals of Improbable Research in Cambridge, Mass, for research that, quote, makes people think, then makes people laugh, then think, unquote. One of my funniest moments in this business happened when I was being interviewed to see whether I qualified for getting access to confidential IRS data. They had to do a security check, and somebody came to my office here in Ann Arbor and interviewed me. And he's looking through my CV. At one point, he looks up and says to me, "Oh, I see here you won a Nobel Prize." Not exactly. After my paper was completed and published in 2009, the US Congress, in its enduring wisdom, repealed the federal estate tax for 1 year and 1 year only in 2010, thus providing the perfect test of my paper. Would people, knowing that the estate tax was about to be repealed, hang on at the end of 2009, and would they or their heirs induce them to pass on at the end of 2010? This led to some guffawing about taxes, and this cartoon, I know it's hard to read, but it captures the issue. It says the estate tax repeal takes effect on January 1st, 2010, but it expires in January 1st, 2011. The planning for Dad's birthday party has already begun, and this is, I guess, the son and daughter thinking about what to do for Dad's birthday. Roller coaster, skydiving, sudden loud noises, warm chicken salad, a marathon. My professional life in taxes, though, has been about much more than death and taxes. About 30 years ago, my eldest child, then about 7, asked me, "Daddy, how can you think about taxes all the time?" As any diligent father would do, I thought a fair amount before replying. And I said, "Annie, it's because tax is about everything. It's about important things you learn about when you grow up, like having a job and investment, deciding whether you'll rent or buy a house." Needless to say, this didn't impress her. But it's true. Tax also matters for decisions that are not entirely economic, like charity, fertility, getting married, death, how much money you will get when I pass on, Annie. I can think about tax all the time because just about everything I think about has a tax angle. Taxes are also about human nature, about what makes us what we are. Are we selfish? Are we free riders? Do we cheat or comply with our tax obligations? And under what circumstances? Is it because we're afraid of getting caught, or we're just resolutely dutiful? How sophisticated are we taxpayers about economic matters? Are we fooled by deficits, by multiple taxes, by the names that taxes are called? And the subject spans both one of the most from one of the most central issues of political philosophy, the proper relationship between individuals and the state, to the most mundane issues of designing tax forms and determining whether bagels are subject to sales tax. In New York City, bagels are taxed if they are sliced and not at all if they are sold unsliced. Think about it. And some taxes are about life. But now, having touched on death and bagels, what is left to say? Well, the last few weeks when I was pondering how to summarize nearly half a century of inquiry into a 20-minute talk, I reluctantly decided I would need to be somewhat selective. So in my last few minutes, I'll talk briefly about three things: how taxes change behavior, tax evasion, and finally, most important, the hunt, meaning how do we learn the answers to these important questions? First, taxes change choices, mostly because they change the price or the reward of just about every choice you can think of. Now, usually this change in behavior is an unwanted side effect, such as income taxes reducing labor supply, reducing investment or saving. Measuring the extent, though, of this unwanted behavior is tricky. Imagine you want to know if taxes go up, how much does the labor supply decline? Well, you can look at episodes after tax increases and see how much labor supply changed. But what you need to know is what would have happened if it weren't for the tax increase. So you can compare what did happen. But of course, we never observe what didn't happen. Now, we economists have developed, I think, impressive statistical techniques to try to tease out answers to these questions, but it isn't easy. Sometimes, though, you can see the effect of taxes. Consider the British tax on windows. Yes, the Brits had a tax on windows from 1697 to 1851. Why tax windows? Well, they were looking for a tax where the liability would be related to how grand the house is. But this was before Zillow, so how did they measure that? Well, first, they tried a tax on fireplaces. More fireplaces, the grander the house on average. The problem is, to measure the number of fireplaces, you have to go inside the house, not for windows. So there was a tax on windows. What happened? Well, we can see the effect on behavior in the United Kingdom still to today, that people bricked up their windows in order to reduce their tax liability. Not only that, but the form of the tax was that there was no tax until there were 10 windows. And then from 10 to 19, I think, there was one tax. And then at 20, a higher tax clicked in. Well, you can look back at the records of the window tax. And what do you observe? A lot of houses with 9 windows. A lot more with 9 than 10. A lot more with 19 than 20. It's got to be because people who owned houses knew how to reduce their taxes. Another example where you can see the effect of taxes: what happens if you tax tobacco, but rather than tax tobacco per unit, like per cigar or per cigarette, you tax by weight? Well, this is a way to get a lot of tobacco and minimize the per unit tax on cigars. Now, sometimes changing behavior is not an unwanted side effect of taxation, but it's the goal of a tax. Let me talk briefly about 2 examples of a tax designed to change behavior. The first one is a year after the window tax, 1698 in Russia, when Peter the Great was trying to emulate Western Europe and noticed that his nobles had beards, which was not the style in Western Europe. He decided to levy an annual tax on beards in order to get the nobility to shave their beards. So, to ensure compliance and perhaps to humiliate those who chose not to shave, those who sported a beard in public had to display it token that they purchased from the tax authority. On one side of the token was the phrase, "The beard is a superfluous burden." On the other side was this, which says, "I have paid my beard tax." Why is having a tax on beards better than just banning beards? Well, it collects some revenue, and also because it ensures that those nobles that really, really wanted to have a beard, it really meant a lot to them, they would pay the tax and have the beard. But those for whom it didn't matter much would shave. Modern examples of taxes designed to change behavior are plentiful. Take the US gas guzzler tax. That's a tax on cars that have relatively poor fuel economy ratings. The amount of the tax varies with the miles per gallon and ranges from $1,000 to $7,700. The worse the fuel efficiency, the higher the tax. Except, as a footnote, SUVs and trucks are exempt from the tax. Wait, what? That's a good illustration that tax policy is not made by economists. The most important current example of taxes designed to change behavior are carbon taxes, whose objective is to slow climate change by inducing businesses and individuals to take into account the social cost of their production and consumption decisions on the climate. At what rate? Well, to get the rate right, you need to know the social damage of burning carbon, and there's disagreement on that, of course. But the mid-range of estimates suggests our carbon tax of about $40 per ton is about right. $40 per ton translates to about 36 cents per gallon of gasoline. Okay, topic 2, tax evasion. The IRS has estimated that evasion of federal taxes is about 15% of what should be paid. Most interesting, they estimate that the rate of evasion is very different by type of income. For income subject to information reporting, like my wage and salary, they estimate the non-compliance rate is 1%. But for income subject to little or no information reporting, like self-employment income, they say it's 55%. What deters people and businesses from evading? Honesty, a sense of civic duty, fear of being caught and punished. Determining the answers to questions like this, I've been working on for a long time, and it's like looking for evidence of the invisible. By its nature, tax evasion is hard to see. If it were easy to see, the IRS could see it. They would catch it, punish it, and people wouldn't do it. So by its nature, it's almost invisible. For some scholars, I think, the fact that you can't measure the thing you're trying to study would be a disadvantage. But I always found it an attraction because it demands creative methods. Which brings me to the third and final thing I want to touch on today, which is the hunt. How to learn about the effect of tax policy. As I've said, it's especially difficult when we're talking about tax evasion, which by its nature is difficult to detect. So I want to tell you about some creative ways of trying to get at this, some of which I did, others which I'm so excited I just want to tell you about. Here's an idea. If you're trying to estimate the difference between evasion of wage earners and self-employed people, get the ratio of food consumption to reported income. This is what the kind of seminal paper on this. It was found that the ratio of food consumption to reported income was way higher for self-employed people. Well, there's two reasons that could be. It could be that self-employed people eat more. That's very unlikely. Or it could be they just report lower income. And that's what makes the ratio of food to income look higher. Here's another clever way, also not due to me. People got access to data from a Greek bank. And these are people who came in and asked for loans. The Greek bank had to decide who to lend money to. Of course, they asked for income tax returns to learn about the person's ability to repay the loan. And they found that the Greek banks made lending decisions as if income on a tax return of self-employed people was about twice what they said. They understood what the average difference in compliance is of self-employed people and wage earners. The second is a topic I've studied quite a bit. Some countries, certainly not the US, in some countries you can go online and learn about the taxable income and tax liability of everybody in the country. Norway, for example, Pakistan, a few other countries. The US won't ever have this. One of the reasons to do it is to deter tax evasion. The idea being, if you report much less than your true income, your neighbor might whistleblow on you. Or if you're a barber, the barber down the street will check out your reported income and tell the tax authorities why they should suspect your reports. Well, the natural place to look for evidence of its impact is to look at what happens when a country institutes disclosure, public disclosure. Does reported income go way up or change not at all? But here's the problem. Countries that do this, they do it for the whole country all at once. And say it happens in 2010. Lots of things happened in 2010. How do you know if you find an increase in reported income, whether that was the reason? So here's two, I think, clever ways to do it, but now I'm talking about my own work, so you can discount that adjective. In Norway, it turns out, they did this all at once, but in some towns before disclosure, the way you learned about it, you had to go to the local tax office and read the disclosures. The local youth soccer team would go in, make copies of these things for the town, and then sell it as a fundraiser. And we know which towns this happened for and which it didn't happen for. Okay, so that hypothesis is, in the towns where you already bought it from the youth soccer team, going online was no big deal. And sure enough, there was a statistically significant difference in the change in reported income in the towns where this was already pretty well known, and in the towns for which this was really new information. In Pakistan, exactly the same problem. And the way you could tell is that in Pakistan, some people have very common names. And in the public disclosure, in the PDF, it just says the name, and then it says what the taxable income and the tax liability is. If you have a name shared by 1,000 other people, if you're at all paying attention, you know that nobody can figure out that it's you. And for other names, they're very unusual. So we could measure exactly how common the name was. And sure enough, we observe an increase in reported income for those with uncommon names. We also now can do randomized controlled trials in economics, which I never thought would happen for tax, because I never thought any country, any jurisdiction, would agree to randomly break up people into groups and have one tax policy for one group and another policy for another. It's never going to happen. But what did happen is that many jurisdictions now randomly impose tax enforcement policies. That is, for example, they'll send letters to a randomly selected group of people and say, hey, we're concerned about your tax filings, and here are the penalties if you're cheating. We do it for you. We don't do it for you. On average, you're exactly the same. If you start to report more, it's a pretty good sign that this policy has had an impact. Well, there's the old-fashioned way of analyzing historical data is the last thing I want to talk about. Let me come back to the gas guzzler tax. So the way the gas guzzler tax is, as the car gets to a higher miles per gallon, the tax falls. But it falls only at the 0.5 decimal of miles per gallon. So if you increase the car's miles per gallon from 17.2 to 17.3, no change in tax. But 17.5 to 17.6 lowers the tax by hundreds of dollars. Same for 16.5, 15.5. So let's look at the distribution of miles per gallon of models in the United States. Well, if you look at that, you can see that it is not a uniform distribution across decimals. In fact, there's a lot less cars at 0.4 to 0.5 than you'd think, and a lot more at 0.5 to 0.6 than you'd think. Why? It must be that when they're designing cars, there's a tax person in the back of the room and says, oh, I see your prototype model comes in at 17.4. Can't you just make the windshield wipers a little bit lighter or change this to aluminum? The tax is going to go down $700. And this is over almost 1,500 models over many years. This difference between the 0.4 to 0.5 and the 0.5 to 0.6 is almost certainly not due to chance. Okay. I hope today I've conveyed what I've loved most about my life in taxes is the hunt, the search for knowledge. Today I've emphasized the fun of the hunt for knowledge about taxes. I've even written a book published last year which conveys insight about tax policy in a lighthearted, often way looking at the history. And this is the cover, which of course I had nothing to do with designing, but which I love. But although I've emphasized the fun and the hunt, we shouldn't lose sight of the fact that getting the tax system right is a critical ingredient in the recipe for economic growth and prosperity, and that the tax system is the most powerful policy tool we have for addressing inequality. These are dead serious issues. Excuse the pun. The goal of much of my research is to inform policy making, to inform the trade-offs that always arise. In the last few years, I've written about the pros and cons of the U.S. levying an annual wealth tax as proposed by Senators Sanders and Warren in 2019. I'm now writing about whether taxing or not taxing capital gains is the Achilles heel of trying to tax the rich more. I'm also now working on measuring group inequity in the tax system, both racial equity and gender equity. Working here at Michigan for the last 35 years has been the most productive environment I can imagine. I've collaborated not only with colleagues in economics in LSA and Ross, but in accounting, law, and marketing. I've directed a research shop, the Office of Tax Policy Research, housed in Ross, which has sponsored weekly seminars, supported student and faculty research, and hosted over a score of conferences. I have chaired or been part of nearly 100 PhD student dissertations, many of whom have also been co-authors and have gone on to be leaders in the field. They now live in 14 different countries, 67 in academia, 20 in government, and 11 in the private sector. They're like family to me. I don't have time today to name all my valued colleagues and invaluable administrators over the years, but I want to express my sincere thanks to them all. I do, though, have time to thank my wife, Ava, who is here representing my actual family. Today, I've tried to give a sense of why I look forward to coming to work every day, but it's because of Ava that I look forward to going home every evening. And to me, that's the key to a happy life. Thank you so much.
Professor Slemrod, if you're willing to come
here?
back up, we are not
Okay.
going to let you go so easy.
All right.
So thank you very much for that wonderful lecture. In addition to talking about your research, I think if taxes were a person, they also got roasted. So really delighted for that. We have time for questions from the audience. I see there's one in the back, and we'll have a microphone for you.
So what is the rationale behind the proposed hiring of 80,000 IRS agents? Is it just a lot of unreported income, or is it sort of manipulating the tax laws on reported income, or what?
Yeah, so the IRS has just gotten a big increase in their budget after many years of declining budget, and the question is about what's the purpose. I think the IRS recognizes that their quality of the service they provide has declined, so I think that's certainly one of their goals. But also, I think they believe they need more auditors and agents to get at the tax gap, the amount of evasion, especially at the top of the income distribution. So I think those are the two key goals, two key objectives in what they're going to allocate their increased funding toward.
Thank you. There's a question here in the front. President Ono? Can you use the microphone, please, for the folks online? Thank you.
This is not a very serious question, but you know your example of in London when they would brick over a couple of windows to get from 10 to 9 or 20 to 19. That must have been because there was a significant jump in taxation by that addition of one, n of
Yes.
1. So you can achieve the same thing, same savings by merging two adjacent windows. Does that ever happen?
Yeah. Oh, two adjacent windows. Okay. So absolutely that happened. So people would, they had two rooms next to each other that now had two windows. You just make the window bigger so it shed light in two rooms. So that absolutely happened. And as is always true in taxation, they passed the law, they observed the behavioral response, and then they changed the law a little bit. So they changed the law to address exactly that situation.
Thanks. We have time for one more question. Actually, I'll slip one in. Was there a hand? So you talked about taxes kind of individually, like there's this tax and that tax. Like, is there interest in kind of taxes as a system, and in particular, like at some point, if there's so much evasion that the whole system itself will fall apart?
Well, certainly we have to look at the tax system using exactly the framework that you suggested. Some people say that we can reduce evasion by having a lot of taxes, not so much each at a high rate. My own view is that that is not a promising avenue. In part because I think a lot of people don't understand the impact of the tax system when it's broken into so many small taxes.
Thank you very much. Let's again thank our distinguished university professor, Joel Slemrod.
Truly fascinating, Professor Slemrod. Thank you so much. And thank you for not talking about provost tax policy. Next, I'm honored to present Professor Lutgard Raskin, an internationally recognized environmental engineer. Professor Raskin works to understand aspects of the microbiome of engineered water systems in order to improve their human health and sustainability impacts. She focuses on the recovery of water and energy from waste streams and the effect of biofiltration and disinfection on drinking water quality. Professor Raskin's research is important for global water sustainability and for concerns like the Flint water crisis. Professor Raskin has advised more than 100 graduate students and has received the university's Distinguished Graduate Mentor Award. Professor Raskin holds the title of Vernon L. Snoink Distinguished University Professor of Environmental Engineering, named to recognize Dr. Snoink, a 3-time Michigan alumnus who was her mentor. Professor Raskin.
Thank you. Oops. Thank you, Professor. Thank you, Provost McCauley. Do I use both microphones? Everything is good? Okay. Well, I'm truly honored to have been selected as a distinguished university professor. And I would like to start by thanking my family, my friends and colleagues, and especially my students and postdocs who took the time to join this event today. But I want to extend a special thank to one more person, my friend, mentor, and former colleague, Professor Vern Snoink, and his wife, Jeannie Snoink, who traveled to be here from Illinois. And as you've heard from Provost Macaulay, I decided to name this professorship for Professor Snoink. He served for many years on the faculty of the Department of Civil and Environmental Engineering at the University of Illinois at Urbana-Champaign, and he became Professor Emeritus in 2005. And you heard he holds degrees, 3 degrees from the University of Michigan. Professor Snoink is a leading expert in drinking water quality control. He's a member of the National Academy of Engineering, and he's been recognized many times for excellence in teaching, advising, and mentoring. I'm going to give an overview of my career's work, and as you can see from my title slide, I'm using the title Managing Microbiomes in Urban Water Systems. So let me start by telling you what I mean by urban water systems. In most urban environments, we take water from the natural environment, treat it in a drinking water treatment plant, and then send the treated water into underground pipes to our homes and our businesses. Then we generate waste, and we send that through sewer pipes to a wastewater treatment plant, and that treated water is typically discharged back into the environment. When it rains, we generate storm water that's collected in our storm sewers, and this water sometimes is partially treated and then goes back into the environment. And finally, that dark green arrow that you see showing up there is a full urban water cycle, because more and more we're starting to reuse treated wastewater as a source for drinking water production. This is happening right now in some parts of the US, in particular in the southwest of the US. What might be surprising to some of you is that microorganisms play a critical role throughout this urban water cycle. We use microorganisms to treat drinking water, to treat wastewater, for example. And so we've started to use this term water infrastructure microbiomes to reflect that. And the term microbiomes has become really popular, so you've probably heard quite a bit about it. But what I mean, for those of you who are not quite familiar with the term, is this very complex, diverse community of microorganisms where we have thousands of different species of microorganisms in one environment. That's a microbiome. And so we observe that in this urban water cycle. In one area of my research, we focus on the drinking water microbiomes with a particular focus on reducing the risk of respiratory tract infections by environmental bacteria that may persist in our drinking water. And in another area of my research, we focus on developing microbiomes and novel biotechnologies to recover resources from urban waste streams. Before I go into more detail on these research areas, I want to share a few personal reflections on how these topics became the focus of my research. Much of my research choices have been driven by relationships with mentors, students, collaborators. And so I want to summarize my approach, my very simple approach really, into these 3 points. First, it's important to allow oneself to be inspired by the work of other scientists, whether it's scientific giants or whether it's new scientists, our students. Second, it's important to learn from role models and mentors, even if they may have had very different life experiences. And third, it's important to recognize the qualities in people that allow for long-term productive relationships. And to deliberately nurture those relationships is equally important. So back in the late 1980s, my husband Eric and I decided to apply to graduate programs in the United States. And we were fortunate that both of us were admitted to the University of Illinois. I knew Illinois could be a great place because it had very strong environmental engineering and microbiology programs, and that's the interface of those two fields is where I wanted to do research at. I didn't know any of the faculty. I did not get a financial offer of support at the time. And so when I arrived in Illinois, it was quite a daunting experience, I must say. During my first week, I met Professor Vern Snoink. He welcomed me. He showed me how I could apply to get financial support for that first semester. And he became one of my most important mentors throughout my career. I met two other important mentors during that first semester in graduate school. They became the co-advisors for my dissertation research. Professor Bruce Rittman, who's an environmental engineer, and Professor Dave Stahl, who is a professor of microbiology and one of the early leaders in the field of molecular microbial ecology. So with Bruce and Dave as my co-advisors, I worked on developing molecular biology tools to study anaerobic microorganisms in natural environments. And for those of you who are not familiar with that term, anaerobic, it simply means without oxygen. So these are microorganisms that can grow and live without any oxygen. I was inspired not just by Bruce and Dave, but also by the work of their PhD advisors. So Dave's PhD advisor was Carl Woese. He was a professor of microbiology at Illinois. And Bruce's PhD advisor was Barry McCarty, a professor in environmental engineering at Stanford. And their groundbreaking work was inspirational to me as a PhD student. I'll tell you a little bit more about that. And as an aside for the students in the audience, check out your own academic tree and read some of those early papers from your academic parents and grandparents. You might find this to be inspiring, like it was for me when I did that as a PhD student. So about a decade before I started my PhD, Carl Woese published a seminal paper in which he introduced the discovery of the archaea. This work was indeed groundbreaking, but it wasn't without any controversy. And it took a few decades before it became part of the mainstream and made its way into biology textbooks. And then during my PhD, a couple of years into it, there was a second seminal paper that firmly established that the archaea were really that third domain of life that he had talked about for a few decades already. Our research group followed these developments very closely. We interacted with people in Carl's lab. We used the work as an inspiration for our own scientific journeys. And one connection between Carl's work and waste treatment was not lost on me. Some of the organisms that he used to discover the archaea were obtained from anaerobic digesters at a wastewater treatment plant in Urbana, Illinois. These organisms were methanogens. They produce methane gas when they're in an anaerobic environment. And a second point that wasn't lost on me was the importance of collaboration, long-term relationships, and giving credit when credit is due. And this is how Ralph Wolf enters into the story. I got to know him when, during my first semester as a grad student, I took one of his classes. And in his research, Ralph developed these very tedious methods to study methanogens. And he provided the cultures to Carl Woese to discover the archaea. So his contributions was really instrumental, but unfortunately, it's not nearly as well recognized as the contribution of Carl. Moving on to the work of my other academic grandfather, Perry McCarty, that was equally inspirational. I was beginning to think about how to expand the use of the molecular microbial ecology tools that I was developing in my research to study wastewater treatment systems. And Perry published 4 seminal papers in 1964, and they remain extremely relevant today. So again, those of you who are interested in this topic, students, go back and check out these old papers and see how relevant they still are. Professor Rittman left the University of Illinois the year before I graduated. And here you see this photo of Vern again, because Vern encouraged me to apply for the faculty position that opened at the time because Bruce had left. So I did, and after a long interview process, I was offered a position, and I served on the faculty for 12 years. So my research group started using molecular microbial ecology tools that I had developed in my PhD research to study wastewater treatment systems. And I decided to focus on anaerobic treatment because that provided an opportunity for recovery of resources from waste streams and a more sustainable approach. In my research, I continued to work at that interface of microbiology and engineering, and so collaborations were really important, and I enjoyed really long-term collaborations with some wonderful scientists and engineers. And our students, here are just a couple of students from those collaborations, really benefited from the co-mentoring framework that we developed. Then around 1990, Vern encouraged me, so you see Vern is there again. He's showing up many times as my most important mentor. In 1999, Vern encouraged me to start working on biological drinking water treatment. His area of research was drinking water treatment, so we're expanding both of our horizons by doing so. And note, 1999 was the year that I got tenure, so I felt comfortable to expand into a completely new area at that time. So I started studying biofiltration. This is an approach that promotes microorganisms in existing drinking water treatment filters. And later that work expanded into studying the impact of disinfection strategies on microbiomes. And so I enjoyed collaborating with Vern. We co-advised several graduate students like Mary Jo Karisitz and Jess Brown. And these are good examples of nurturing long-term relationships. I'm still collaborating 20 years after they graduated with both Mary Jo and Jess. In 2005, Eric and I moved with our 3 children to Ann Arbor to join the University of Michigan. You have heard about Vern quite a bit already. He's going to show up here one more time because after I moved to Michigan, he invited me to a workshop that he was giving at the City of Ann Arbor Drinking Water Treatment Plant. And so thanks to Vern, I got to know people like Larry Sanford, who was the water quality manager at the City of Ann Arbor Water Treatment Plant. And we became close collaborators. And since 2005, I've been working with the city. My students have done as well. And so I'm particularly thankful to Brian Steglitz, Sarah Page, and most recently Becky Lahr for these collaborations. We've co-advised many students and postdocs, not just with the input from people at the plant, but with faculty collaborators from various units across campus, as well as several of my engineering colleagues. And I've summarized the many students and postdocs that were advised and co-advised by the people you just saw who actually worked with our City of Ann Arbor collaborators. In much of the work that these students worked on, we focused on opportunistic pathogens. They are a growing concern in drinking water, and they cause infections in people with weakened immune systems. They naturally occur in the environment, and once they enter the drinking water treatment system, it's hard to remove them. They tend to persist and replicate. You have probably heard of Legionella pneumophila. It's an opportunistic pathogen that causes Legionnaire's disease. In our work, we focus primarily on non-tuberculous mycobacteria, or NTM. They're present in 80% of our drinking water across the US. And in Ann Arbor, we certainly also have NTM in our drinking water. There are several studies that have suggested that the presence of some NTM in drinking water is associated with respiratory tract infections. The links are not that well established. In a recently published study that was led by my former postdoc, Yoon Shen, we made some progress towards understanding the potential importance of NTM in infection. And I prepared a couple of slides based on Dr. Shen's work. So you can see already here that she performed experiments in which we collected air samples before, during, and after showering in a bathroom. So field work in the bathroom. The plot that you see here is a very simplified version of the results, and I see that some of the text disappeared. So the first bar represents the microbial community in the air before showering. So you only see a few gray bars, suggesting that there's only a few important groups of microorganisms present in that air. The second bar represents the community during showering. So you see more gray bars showing up. And Yoon demonstrated that those groups of organisms that were added to the air originated from the shower water. And you also see a red bar representing the non-tuberculous mycobacteria. So she demonstrated that those were present in the air during showering. And then we used a different technique to quantify the NTM concentrations in air before and during showering. And you see that the numbers are quite low, 250 cells of NTM per cubic meter of air in the bathroom before showering. During showering, that number goes up to about 4,000. And you can calculate what that means for us when we take a shower. So we breathe in about 8 liters of air per minute. So if you convert that, you would inhale about 30 cells per minute of showering. We don't know if these organisms are alive. We used DNA-based approaches to quantify them, and DNA can stay around even if organisms are not alive. So to evaluate whether they were viable cells, we use a technique called flow cytometry to visualize all the live and dead bacteria in our samples. And so here you see a typical plot from a flow cytometer for the shower water. And the dots represent bacteria, so lots of dots, lots of bacteria in these samples. And these areas indicate the location of live cells versus dead cells. So you see a substantial fraction of live cells in shower water. When we look at the same plot for shower air, so air collected during showering, you see that there's no live cells. So that's good news. We hypothesized that the bacteria that were transferred from water to air were damaged during this process of aerosolization. And in our next experiment, Dr. Shen took air samples and incubated them in a culture medium that simulates human sputum. And what she found was that these damaged cells were able to be recovered. So they were still alive, they were a little bit damaged, they appeared dead, but they weren't quite dead. And so you see an increase of 3 orders of magnitude after 5 days of incubation in this medium that represents human sputum. So we didn't make the next step. We didn't connect this observation to infection, so we don't know if these cells are indeed infectious. That requires future research. Our ultimate goal is to engineer the drinking water microbiome to reduce infections. That's a tall order, but we are continuing this work. We're using the treatment strategies that we've been using for a long time in the drinking water treatment field, and are combining them with microbial ecology approaches like directed evolution. And this is work that we are beginning to develop with Amit Pinto as the PI. He's a professor at Georgia Tech, and one of our colleagues here from chemical engineering, Nina Lin. All right, switching gears a little bit. You heard earlier that my research group started studying anaerobic waste treatment systems when I started my work at Illinois. So soon after I moved to Michigan, I met Steve Skurlos from our mechanical engineering department. And we decided that we would continue this line of research. Steve's whole career has been focused on sustainable design approaches. And so his expertise is very complementary and helpful for this field of research. One other connection, Steve obtained his PhD from Illinois. So we actually knew about each other before I even moved here. There's a couple of other collaborators that I just want to briefly mention who have been instrumental in co-mentoring graduate students. Samir Kanal from the University of Hawaii and Ilse Smets from KU Leuven, which is my alma mater in Belgium. And I have a similar slide here for all of the postdocs and students who've worked on studying and developing anaerobic bioreactors since I moved to Michigan. And I'm just giving you one snapshot of the work that some of them have been working on. We have a Department of Energy funded project. Steve Skirlo is actually the co-PI on this grant as well. I'm going to tell you just briefly what that project is about. This schematic you've seen a few times. You see this black box there where different waste streams are going towards. So we have food waste going into this black box. We have solid waste from wastewater treatment plants, byproducts really of wastewater treatment that can go into this black box. And we are developing a process that can produce high purity biomethane. It's basically the same as natural gas, so you can use it directly in the natural gas grid. We would like to produce this biomethane at the lowest possible cost, lowest environmental impact, and we also would like to do all this by treating these waste streams. So it's not just about recovering resources, it's also about treating waste streams that need to be treated. They cannot be discharged into the environment. So I'll open this black box briefly for you. This black box consists of a complex integrated system. At the bottom, you see a two-phase anaerobic dynamic membrane bioreactor that we are working here, we're developing here in Michigan. And then at the top, you see a schematic that simply represents a combined electrochemical biological system that's being developed by Argonne National Lab and Northwestern University. And so we are producing biogas at a very high yield, and that biogas goes into this integrated system to produce the high purity biomethane. And when we look at this system in a little bit more detail, the first phase of that system is designed to mimic the stomach of a cow, which is called a rumen. So this rumen environment is really ideal to hydrolyze difficult to degrade material, to make that recalcitrant material that ruminant animals eat more digestible. And so we're taking advantage of that environment. So we've designed a bioreactor that has the same hydrodynamics and chemical conditions that you might find in the rumen. And we're seeding that with the microbiome from the rumen. And then you can see what this prototype looks like in the lab. The effluent from this, or the first treatment effluent from that reactor goes into our second phase reactor. And that's a novel design that our team came up with. It has a tree-like structure in it, and it allows, through some other novel characteristics, to produce biogas at a much higher rate than a conventional system, and it does that with very little energy input for controlling fouling. We have some preliminary data at the left, our data from our study. I don't want to go into details, but we're basically demonstrating that we can get the same results as competing technologies, both for methane production and for organics removal, waste treatment. But we're doing this at much lower energy consumption. So we're going to evaluate this system first at Argonne National Lab. We're going to integrate all of these pieces of the system at Argonne National Lab at the lab scale, and then we'll build a pilot scale system the following year at the Detroit wastewater treatment plant. So the Great Lakes Water Authority is co-funding this work together with the Department of Energy. And because our preliminary results are really promising, we're very hopeful that that scale-up will be successful. So I'm hopeful that with my brief overview of my career's work, you have gained some insights in the complexity of microbiomes associated with urban water systems. As you've seen, there's pathogenic microorganisms that are difficult to remove from our drinking water systems with our current treatment strategies. But fortunately, the vast majority of microorganisms play positive roles. They help us with water treatment and resource recovery from waste streams. And I would like to end by reiterating that much of my work is being supported and made possible through long-term relationships with mentors, tutors, and collaborators. And I would encourage all students and junior colleagues who are here to spend time finding mentors, nurturing those relationships, and I would encourage senior colleagues to pay it forward by serving as mentors. Thank you very much for your attention, and I'm happy to answer questions if there is time.
Thanks very much, Professor Raskin. We have time for questions from the audience. Great. Microphone is coming.
Thank you. I'm curious, if I remember right, there's close to 1,000 different species of bacteria in the human digestive system. And I'm curious, in the wastewater, presumably there's a big overlap, but perhaps unique bacteria in both locations. And I'm curious if you would comment on the differences between the two.
Right. So great question. When you start looking at raw wastewater that's entering the sewer system, you are going to find a lot of the similar organisms that you would find in our waste. When that consortium of microorganisms enter a wastewater treatment plant, you are generating operating conditions in the reactor that are designed to treat the wastewater. So we're creating a very different environment. So while we maintain a lot of these populations, the relative abundance of them changes greatly. And so we're basically selecting for organisms that help us with treatment by creating the operating conditions in those bioreactors. And so when you look at the microbiome in a wastewater treatment plant, at first glance, it might look quite different from the microbiome in your gut. But when you start digging into it, you'll find similar populations still present.
Thank you.
Next question. Thanks. I have a question about your collaborations with the municipal facilities, like the City of Ann Arbor. That's a wonderful form of public engagement, but it seems to advance your research. Can you talk a little bit about both the rewards or maybe the frustrations of those kinds of relationships?
Well, I can't talk about the frustrations because it's been a wonderful experience. And I mean, I wouldn't say this is going to be the same for every city, but certainly in the city of Ann Arbor, we have amazing professionals in our city, and they're the best collaborators. They have never asked us not to publish a finding, even if it was controversial or difficult for them to deal with. Their philosophy is, the more we know about our water, the better off we are, the more proactive we can be to make progress and treat our water. And that is truly what we have experienced. But I've heard stories from other researchers who try to collaborate with other cities, and it's not always straightforward. Yeah.
Thank you very much. Please join me in thanking our distinguished university professor, Lute Raskin. This concludes our session. I understand we have a reception that available, so we would for a gathering and also some additional opportunities for questions with our speakers. And let's just take a moment to thank and congratulate all three of them once again on their distinguished university professors. Have a great evening. Thank you.